Hello and welcome to our video lecture on functional evaluation and linear functions. We learned about functions and functional notation in our last video. In this video, we're going to focus on evaluating functions for a given input value, and we will also study a type of function which we are already familiar with, namely linear functions. When you evaluate a function for a given input value, that's called functional evaluation. Functional evaluation, or evaluating a function for a given input value, simply means finding the output of the function for the given input value. In the following example, we'll find f of 3 for three different kinds of functions. Here we have a function f, and notice we're using the same name for different functions, and that's completely the norm, and it happens all the time. So in the context of a particular problem, it'll be clear what the function f represents. So here we have a function f which is mapping the number 1 to the letter A, the number 2 to the letter B, and the number 3 to the letter C. So when we're asked what is f of 3, we mean what is the output of this function when the input is 3. So we look for the ordered pair with the input location being 3. Notice each of these ordered pairs is in the form of input comma output, right? So this is the ordered pair where the input is 3. We can see the output of this function will be C. We have another function here. This time it's depicted in tabular form, or in the form of a table, and we're asked for f of 3 as well, right? So again, we have to look in the input column for the input 3. So we see it right here, and now we're going to find the output, which is of course this corresponding number right here. So that'll be -3. All right. How about for this particular function depicted graphically? So we want f of 3. So notice that we always agree on the x-axis being the input axis and the y-axis being the output axis, right? So we look at 3 on the input axis, and then we go straight up till we hit the graph. Then we want to go straight left till we hit the y-axis, and right there we'll see that this point right here on the graph of this function corresponds to the pair 3, 7. So when the input is 3, the output is 7. All right, so here we have another function. This is actually what we refer to as functional notation, and even though we represent functions in different formats, this is by far the most common way that you're going to be seeing functions from this point forward. These are really useful when it comes to teaching the concept of functions, but once we have gotten comfortable with the concept, we're going to be mostly using this rule variety for defining a function. So here we have f of x equals 3x minus 2. In other words, what this function does to an input, any input you feed it, is it's going to triple it and then subtract 2. So what is this function going to do to 3? Well, remember, functions are very, very boring entities, in the sense that they only know one thing and they do it extremely well. So very, very good servants for us, functions, because they do what we need them to do. And of course, when it comes to a machine that you're designing, you would want the machine to do exactly what that machine is supposed to do, right? And that's where functions come in. A lot of the machines that you use in your life, they are basically ruled by a bunch of different functions, okay? So we're learning about these structures here now, and then you'll learn more complex versions as you proceed in your field of interest. All right, so here we have f of 3, remember, they do one thing, but they do it extremely well and extremely consistently, these functions. So it's going to do the same thing, triple it and then subtract 2. So it's going to take the 3 and triple it and then subtract 2. So you get 9 minus 2, which is 7. Okay? So that's what f of 3 is. For example, if you wanted f of 0, what would you do? Well, you would plug it in here for x, so you'd get 3 times 0 minus 2, so you'd get 0 minus 2, which is negative 2. If you wanted f of 1/2, same business. Remember, this function only does one thing. You feed it something, it triples it, and then subtracts 2. So here, it's going to triple the 1/2 because that's what you're feeding it now. Then subtract 2. So you get 3/2 minus 2, which you can write as 4/2. So it's basically negative 1/2. So that's what the output of the function would be if the input were 1/2. All right, so this is how we perform functional evaluation. As I mentioned on the last screen, most of the functions we will encounter will be of the last variety, which was described by a rule. And the rule defines the relationship between the input, which we call the independent variable, or in most basic examples, the variable x will be used for that, of the function, and the output of the function, where the letter y is used, and that's also called the dependent variable, because you substitute a value for x, then find out what value you get for y. So the value of y depends on the value of x. This is the logic for calling these y the dependent variable and x the independent variable. Of course, those are just one pair that we have chosen to traditionally represent these, but as you go into different fields such as electronics, etc., you will use different letters for input and output of functions, which are more relevant to the field of knowledge that you're studying. So here's an example of a nonlinear function. Basically, that means a function whose graph is not going to be a straight line. And the reason for that, of course, is because you have this square here. Remember, linear functions, the highest power that you see is the first power of a variable. And we're going to be doing some evaluations, but it's done very much similar to the way it's done for linear functions. So if we want f of negative 1/2, we're just going to substitute negative 1/2 everywhere we see x in the definition of the function f of x. So we get 3. Now, because it's negative, you're going to want to parenthesize it and then square it, right? Because you want to square all of negative 1/2, not just the 1/2 part, all right? Or just the 1 part for that matter. All right, so plus 2 times, again, I'll go ahead and parenthesize the negative 1/2 minus 1. So we end up with negative 1/2 squared, of course, is going to be 1/4 times 3 will give us 3/4. And then this 2 times this negative 1/2, positive times negative will be negative. 2 times 1/2 is, of course, 1, right? And then we have a minus 1 at the end that we don't want to forget either, right? Just like that. All right, so notice we have negative 1/2 squared, quantity negative 1/2 squared, which is 1/4 times 3 gives us the 3/4. This positive 2 times negative 1/2 is where the negative 1 here comes from. And this negative 1 is just the original negative 1 that was in the definition of the function. So here we end up with 3/4 minus 2. And we need a common denominator, so we'll go ahead and write the 2 as 8/4. Basically, what we have here is 2/1. The LCD is 4, so we need to multiply the top and the bottom by actually not there, but on the top one by 4, like so. That's where we get 8 over 4. So we get 3/4 minus 8/4, which is of course negative 5/4. So basically what we just found is that f of negative 1/2 equals negative 5/4. All right, so now let's go ahead and find f of 2. As always, once you really understand what's going on, pause the video, try it on your own, then proceed. Always be in interactive learning mode if you really want to learn something. All right, and that's not just for math, it's for any class. All right, so here, I hope you tried this already. You're going to get 3 times, even though it's negative, I can still use parentheses. It's a very convenient way for me to handle both multiplication and substitution. So plus 2 times 2 minus 1, right? So we end up with 3 times 4. We have to square first, remember, by the order of operations. So that's 12 plus 2 times 2 will give us 4 minus 1. So that's 16 minus 1, right? Which is 15. So we just found that f of 2 is equal to 15. That means the output of this function is 15 when the input is 2. Now we want to find f of x plus 1. Now you may think that's a little bit strange, but that's very, very common, right? We still are finding a variable expression for the input, and all we have to do is basically a substitution. Wherever we see x, we're going to replace it with x plus 1, right? On this definition on the right side of this function f of x. So we're going to get 3, and instead of x, we're going to put what? X plus 1. And then we're going to square that, plus 2. And remember, we're going to multiply that by x plus 1 again, minus 1. Now it's just a matter of simplifying that. Now x plus 1 squared, of course, we can quickly work out using a table, or if you know a formula for it, you can use the formula. I like the table because it's quick and you don't have to memorize anything. So we get x times x, which is x squared, plus x times 1, which is x. And then here we get 1 times x, which is plus x, and then 1 times 1, which is plus 1. And of course we combine those, so we get x3 times x squared plus 2x plus 1. And then now we're going to distribute this 2, so plus 2x plus 2, right? Distribute the 2 minus 1. Okay? So now we'll go ahead and distribute the 3 as well. So we get 3x squared plus 6x plus 3 plus 2x. Let me go ahead and combine those. That's plus 1, right? 2 minus 1 is 1. All right, so now we're going to combine like terms. So we have a 3x squared, which is not like anything, so we'll write it. 6x is like 2x, so they can be combined, so we get plus 8x. And 3 is like 1, so we get plus 4. And remember, what we have just found is f of x plus 1. And that's it. There it is, f of x plus 1. Okay, so that's how we handle these functional evaluations. Now we would like to focus the rest of the video on linear functions, which are a very important class of functions encountered in many fields of science and mathematics. The definition is simple. Any function that can be written in the form f of x equals mx plus b, where m and b are real numbers, is called a linear function. Now, you may have seen this before or something similar to it with y in place of f of x. And it's essentially the same structure that we're seeing here, but we are now treating it in the context of functions. In fact, to graph a linear function of the form f of x equals mx plus b, all we have to do is replace the f of x with y, and we'll end up with y equals mx plus b, which is the familiar slope-intercept form of the equation of a line. Then we'll go ahead and proceed by graphing that equation, which we already know how to graph, we do so by plotting points of the form xy. We call the solutions of this particular equation, which is a linear equation in two variables. Let's see all of this in an example. So first thing we want to do in this example is determine if this function right here is a linear function. And of course we can see that if you have f of x equals 3x minus 2, then we can easily notice the fact that this can be written as 3x plus negative 2. So compare that to f of x equals mx plus b. We notice that m here is going to be 3 and b is negative 2. So we have demonstrated that this is indeed a linear function. Now, normally we don't go through all that. We recognize the fact that even though it says plus b here, a negative number can easily be handled in this manner, and therefore we can call that a linear function without having to go through all that. All right, so now we want to find f of negative 1, which of course we can find very easily by substituting negative 1 for x in the definition of the function. So we get 3 times negative 1 minus 2. So we get negative 3 minus 2, which is negative 5. So there is f of negative 1. Then we want to find f of 3x. This is just giving us some practice with functional evaluation. Remember, every place we see x, we're now going to replace it with 3x. So instead of 3x, we're going to have 3 times 3x, and then minus 2. So now we end up with 9x minus 2. So that's f of 3x. If we want f of x minus 1, we're going to replace x in the original definition with we're going to replace this x with x minus 1. So we get 3 times x minus 1. And don't forget there is a negative 2 here, so, or a minus 2, so we put minus 2 as well. All right, so now we're going to simplify that. So we get 3x minus 3 minus 2. So that is 3x minus 5. So that is f of x minus 1. All right, so now we want to find f of 5x plus 6. If you haven't already paused the video to try some of these on your own, definitely do it now. Go ahead and try to find f of 5x plus 6, see what you get, then come back. All right, welcome back. I'm sure that you replaced x with 5x plus 6, hopefully, right? So the x from here gets replaced with this 5x plus 6 because that is f of x, but we want f of 5x plus 6. So we're just doing a substitution. So we end up with 3 times 5x plus 6 instead of 3x, and then there's a minus 2, right? So we end up with 15x plus 18 minus 2. So that is 15x plus 16. Notice that that is f of 5x plus 6. All right. So the last thing is, if f is linear, then go ahead and graph it and determine its domain and range. Now remember, in order to graph that, we're going to take f of x equals 3x minus 2. We're going to replace the f of x with y. We're doing a substitution there. And now we're going to, actually that's just 3. And now we're just going to graph this linear equation, which is very simple because we know the slope is 3. And the y-intercept, which is going to be the ordered pair 0, -2. Remember, the b in f of x equals mx plus b, that's the y coordinate of the y-intercept. The y-intercept itself, of course, is a point in the plane, so it's an ordered pair, but since it's on the y-axis, the x value is going to be 0, right? So now all we have to do is do this simple graph. So let's go ahead and bring in a grid and we'll graph it. We know that the y-intercept is 0, -2, so that's a good starting point to plot our graph. All we need is one other point, of course, because 2 points determine a line in a plane. That means given 2 points, distinct points in a plane, there's only one line that goes through them. So all we need is to come up with one other point. And of course the slope will take care of that for us very easily, because the slope is 3, which can be written as 3 over 1. So the delta y is 3 and the delta x is 1. The change in y is 3, the change in x is 1. So from here we're going to go up 3 units, 1, 2, 3, and then to the right 1 unit, and then we can graph our line. Now notice that that will land us at the point 1, 1, of course. And there is our graph. As far as the domain and range, of course we can use any x value to plug into here, so the domain is all real numbers, and consequently we're going to end up getting all the y values on the y-axis as well, eventually, as y coordinates of points on this line. Therefore the range, or the set of outputs, will also be the set of real numbers. So the domain and range are both, let's try that again. So the domain and range are both the intervals negative infinity to infinity, which is just another way of saying the set of real numbers. All right, so there's a nice example for a linear function and several different tasks that give us some good practice with that. So let's go ahead and look at some more. All right, for this problem, we're doing a similar type of example, but here we have some fractions which make no difference because remember, it is in the form mx plus b, and all these two numbers need to be, these two constants, they need to be real numbers, which they are. So this is definitely a linear function. Now it says if it is, then go ahead and graph it and determine its domain and range. So again, what we're going to do is we're going to go ahead and replace f of x with y. And at this point, we're going to go ahead and come up with 2 points that help us graph it. Now, whereas we could do the slope-intercept approach like the one that we used in the previous problem, but because of the fractions, it might be a little bit easier if we actually make a table of values and plot those instead. With these types of problems containing fractions, if you're patient and try a couple of numbers, you may end up with some really nice results that don't even contain fractions. For example, if I were to substitute 0 here, I would end up with a fractional value for y. But if I substitute 1 for x, for example, I notice that I would get 2/3 times 1, which is just 2/3 minus 5/3. And of course, in other words, if x equals 1, we end up with 2/3 minus 5/3 for y, which is of course negative 3/3, which is negative 1. See, that's a very nice result. And if we substitute 2, we're going to end up with 4 minus 5, which is negative 1/3. That's a fraction. But notice that 3 will not get us a whole number either. But if we go to 4, we get 8/3 minus 5/3. So if x equals 4, we end up with y equals 8/3 minus 5/3, which is also a nice 3/3, which is 1. So you don't always end up with this, and it's perfectly okay to work with fractions and plot fractions, etc. But sometimes if you just be a little bit patient, you can come up with some really, really nice results. So 4 will give us 1. Now we're just going to plot these 2 points on the Cartesian coordinate plane, and we'll have our graph. All right, so here we notice that we have 1, negative 1, and 4, 1, and we graph our line. We notice once again that the domain will be all real numbers, and so will the range. Now, this is not accidental. This is actually the case for all oblique lines, right? Remember, oblique lines are lines that are neither horizontal nor vertical. For all oblique lines, we know that the domain and range will always be the set of real numbers. We know that they're all functions because they all pass the vertical line test, and therefore this is a very typical linear situation. Now, horizontal lines are also qualified as functions, because those we'll study in a minute, will pass the vertical line test. But the only kinds of lines that are not relations, which can also be called functions, are vertical lines, because they of course miserably fail the vertical line test, given that a vertical line, namely themselves, will go through them many times, in fact infinitely many times. But as long as a line is neither horizontal nor vertical, it will definitely be a function, it will definitely pass the vertical line test, and it'll definitely have domain and range, which basically will be all real numbers. One of the things that we would like to be able to do sometimes is to write an equation in two variables, which is linear, as a function. Now, this does not necessarily only apply to linear functions, but right now we're going to be focusing on that. So this can be, of course, accomplished by just solving for the dependent variable, which we usually label as y, in terms of the independent variable, which we usually label as x. So here's an example that we can try that on. So we're going to take this linear equation. Of course, if you recall from the discussion of linear equations, this is not in the slope-intercept form that we've seen today. This is in standard form. So what we would like to do is take this linear function in standard form and write it in functional notation. In order to do that, what we're going to do is we're going to go ahead and solve this linear equation in two variables for y. So we start out with 3x minus 4y equals 12. We'll go ahead and move the x to the other side, the x term, so we get negative 4y equals, remember, change sides, change signs, because we're basically just subtracting 3x from both sides. So we end up with negative 4y equals negative 3x plus 12. Now we need to go ahead and get rid of this negative 4 to get y by itself. So we're going to divide both sides by negative 4. And of course on this side it splits, right? So we might as well save one step and just take care of the split. Alright, so we end up with y equals now negative 3 over negative 4. That's going to give us positive 3/4 x, and then positive 12 over negative 4, that's negative 3. Now, once we've solved it for y, in order to get this into functional notation, all we have to do is go ahead and interchange y with f of x. So instead of y, we're just going to write f of x equals 3/4 x minus 3. So we just took a linear equation in standard form and we converted it into a function, which is a nice thing to be able to do, because now if we want to evaluate this function at any given point, all we have to do is plug it in for x here. So for example, f of negative 1/2 is going to be 3/4 x. So 3/4, instead of x, we're going to substitute negative 1/2 and then minus 3. So we end up with negative 3/8 minus 3 over 1. We need an LCD to go ahead and combine those, which is of course 8. So this one is already good to go. This one we need to multiply top and bottom by 8. So we end up with negative 3 minus 24. So negative 27 over 8. So what we just found is f of negative 1/2. All right, f of 0, that's going to be easy. We're just going to substitute 0 for x, so we get 3/4 times 0 minus 3, which gives us, this is going to of course become 0. 0 minus 3 is -3. And f of 2.5 is going to be 3/4 times 2.5 minus 3. So we can go ahead and utilize the help of our calculator for that. So we get 3/4 times 2.5 minus 3. So if I go ahead and transfer that back into fractional form, we get -9/8. Of course, you can do this manually too. That'll be great practice for you anyway. All right, so there we have it, right? So now all we have to do is go ahead and graph it and state the domain and range. Of course, notice that we have the pairs of the ordered pairs that we need to graph this. We have more than enough because we only need 2, right? So we can just use, for example, this nice easy one. When x is 0, y is -3, or f of x is -3. And when we can also say plot this one. When x is -1/2, y is -27/8. So let's go ahead and plot that. You should pause the video, see if you can get a good graph of that, and then we'll return to check. All right, so here we have plotted the points 0, -3, as well as -1/2, -27/8, which actually turns out to be around this much in decimal form, okay? And you can see the line that goes through those 2 points. Of course, this is an oblique line, so notice if you trace back all the x values that correspond to this line, you'd get the entire x-axis, and if you go back to all the y values that are corresponding to this graph, you'll eventually end up seeing all the y values on the y-axis. So both the domain and range, once again, not surprisingly, are the set of real numbers, given that it is an oblique line. So we will now just state the domain and range. -infinity to infinity, and the range also the interval from -infinity to infinity. Notice that if you were to write those in set builder notation, they wouldn't look identical. They would look slightly different, because this would be the set of all x such that x belongs to R, right? But this one would be the set of all y such that y belongs to R. So even though they look identical in interval notation, they do look distinct in set builder notation. All right, and that is how we would handle a problem like that. We basically can take a linear equation, turn it into a linear function. We can do functional evaluation, and of course we can graph it. And when we do, the y-axis is the same as the f of x axis. So oftentimes you may see on the top of the y-axis, y equals f of x, like so. Okay, so that was not that would not be a rare thing. You would see that often. All right, we want to close today's lessons with a special kind of linear function, which we already hinted at, and those are constant functions whose graph actually end up being horizontal lines. And the reason we call them constant functions, of course, because the output is always going to be b regardless of what the input x is. So let's take a look at an actual example. All right, and this is in fact our last example of the day. This is kind of a nice short lesson. We want to verify that this function is in fact linear. Remember, to show that a function is linear, all you have to do is it can be written in the form of f of x equals mx plus b, where m and b are real numbers, and x of course is a real variable. All right, now we're going to try to do that for this function. Notice I can write this as f of x equals when I notice there is no x term, right? So but that means I can always write 0x plus 5. So notice m is 0 and b is 5. So we have verified that it is in fact linear. Its graph should be a straight line, and of course we know it is. In order to graph it, as always, we take f of x equals 5, interchange f of x with y, and now graph it. So let's go ahead and graph that. Now you should remember how to graph those, because this is going to be all the points in the Cartesian coordinate plane whose y coordinate is 5. Think about that, plot it, and then let's compare our graphs. All right, so here we have the graph of f of x equals 5 or y equals 5 that we're familiar with. We know it's a horizontal line going through 0, 5. Now, here we have shown a few points. Notice that if we make a table here, we would have something like this, right? So when x is, for example, -2, what's f of -2? Well, it's going to be 5. Remember, this is a constant function. What's the f of -1/2 or -0.5? That's also going to be 5. What about f of 1/2? That'll be 5 as well. And f of 2 will be 5. These are just a few points in the plane whose y coordinate is 5. If you want all the points in the plane whose y coordinate is 5, of course, you would end up with that entire line, right? And that's why that's the graph of f of x equals 5. Now, the domain, of course, remember, any x value can be the input here. So the domain is, as usual, all real numbers. Notice that the range here is by no means all real numbers. It's very limited. Remember, the range is the set of all the outputs, and this function sends every real number to one number, 5. So the range of this function actually consists of a single real number, 5, and that's it. So these are interesting functions. They're called constant functions. They're also linear, of course, because when you graph them, you do get a straight line. You get a straight horizontal line, right? And it does, of course, pass the vertical line test. No vertical line would cross it more than once. So visually, you can verify that it's a function as well. And that's about it. So this is how you handle a constant function. And that pretty much wrapped it up for us today. So make sure that you understand these important functions, and stay safe until our next video.